Hi, my name is Jesus Ramirez from Singularity Engineering. Today, I am going to talk to you about Airlift Bioreactor. Also, I am going to explain you why CFD is a very important tool in the bioreactor's design. Also, I am going to talk to you about how we can use CFD for the scale-up process of this equipment. An airlift bioreactor can be defined as a pneumatically mixed reactor which is widely used in chemical, petrochemical, and bioprocessing industries such as fermentation. It is also one of the most important reactors for biomass and energy production. In this type of reactor, the mixing process has a significant effect on the performance. Also, how light energy is delivered to a microalgae cell plays a significant role in determining how effectively such energy can be converted into biomass. It is known that the light intensity always reduces exponentially from the wall to the reactor center following the Lambert-Beer law. For instance, the light exposure history of a cell is eventually determined by the movement or the trajectory of this cell inside the reactor. However, determining the representative trajectory of an algae cell in the reactor is not trivial. According to the before mentioned and to our area of interest, the following question arises. How can CFD help the bioreactor's process design? CFD can help bioreactor designers in different ways. For example, it allows you to model multi-phase flows as deployed in Airlift Bioreactors. Also, it allows you to calculate or predict different flow fields that experimentally are not easy to measure. For example, shear stresses, vorticity, velocity gradients, among others. In the same way, algae cell trajectories can be predicted by using the appropriate models. Finally, using CFD allows you to do virtual prototyping processes as well as scale-up studies. This helps the designing divisions to accelerate their processes. The geometry I am going to use in this video is the same that used Leeuwen in his study in 2011. The geometry is an airlift bioreactor with a circular sparger like this one here, which input air into the bioreactor. The bioreactor is composed by two concentrical pipes, one external pipes, this one, and one inner pipe, this one, that is the riser. Then the airflow goes through this pipe, is going upwards. Here we have the free surface level of the water, then the air comes here, then it's the gas by the free surface and exit the bioreactor, and the water is moving by the motion of the air, moving like forming these circuits. Okay, then this is the principle of working of this kind of airlift. In this video, I am going to explain two ways of simulate this kind of bioreactors. The first one is related with the geometry one, that is a complete geometry with free surface modeled. The second one, the geometry 2, is a half-cut geometry with a gas in boundary condition. The second geometry has the advantage of have a lower value of cells in comparison to the geometry 1. And as you can see here, if I use the gas in boundary conditions, I am not going to model the free surface, which allow me to use a lower amount of computational resource also. Then I am going to explain both both geometries, and also I'm going to use different models for each geometry, which I'm going to explain and show you the results I got from this model. Well, here's the first geometry open. I am already in the Fluent setup. Then I'm going to show you how to set up this kind of cases. And this is a way, this is not the only way you can use for simulate this kind of Airlift Bioreactors. It's just as a way I'm going to explain it to you. Okay, then, well, in general, in this case, I prescribe a steady simulation, but I'm going to use a pseudo-transient model. Then this setup could be used initially a well initial estimation, and then once you have your results, you can change into the transient simulation because this phenomenon is inherent transient. Okay. Then I'm going to use a multi-phase model. Then I have it enabled. I'm going to show you which one I'm going to use initially. I'm going to use the volume of fluid model because I am going to model the freezer phase among the mixture of air and water and the air per se. Then I'm going to use the volume of fluids with the Eulerian phases. I'm going to use in this case the implicit formulation. Of course, if you want to use the explicit formulation, then you have to change your simulation to a transient one. Okay, I'm going to use implicit body forces, and I want to use a sharp interface modeling. I want to have a good accuracy and resolution in the first phase, and also that's the reason I enable the interfacial anti-diffusion option. Okay, the phases I use is water, um, on Earth. Water is my primary phase, and air is my secondary phase. Then I name it. This is the water. This is the air. Okay, and the phase interaction. I am going to use a surface tension coefficient, a constant value. In this case, I just left 0.6, but you can change it. For example, a well recommended value for surface tension among water and air is 0.072. Yeah. Then in this case, I use this. I got some results, but you can change this. Yeah, a more in-depth knowledge of this value you must have before put this value here. Okay, then this is just a value for demonstration, but not with the rigorous on the physical behavior of the interface. In heat and mass reaction, none of them are modeled because the case I want to simulate or model does not have this kind of interactions. Okay, then we click apply and close. Once you have set up the multi-phase model, then you go to the boundary conditions. Okay, then you see the inlet. The inlet for me is going to be the sparger, that is the one who is injecting the air. Then I double click the sparger. As you can see, it's a velocity inlet boundary condition. In this case, this is a velocity of 0.38 meters per second. Um, it is entering to 300 kelvins, but I'm not modeling in this case the heat transfer processes. Then I just left this value by default. Okay. Then as I am working with a multi-phase flow and I am using the BOF model, then I have to set up also boundary conditions for the water and for the air. Then I double click water, and you see that it is nothing to do here. It's just uh, we is the setup presentation. And in air, in this case, you have to put the volume fraction. Then this case is 1. I want only to inject the air through the sparger. Then the water is entering to the domain through the sparger. Okay. Then we have some internals uh, boundaries that this is because of the way of the geometry was performed, and the outlet is a pressure outlet. Okay. Then I have the water is the same that for the velocity inlet, nothing to do here. Remember, just foresee that the pressure outlet is a gauge pressure outlet of 0. This is atmospheric pressure. Okay, and in the air, I prescribe the backflow volume fraction of 1. Then is we have backflow in the solution. The volume fraction of that backflow is going to be only air. Okay, that is the upper part of the bioreactor. Okay, then I am going to select the methods. I am going to use the coupled methods, and it's what I was saying, a pseudo-transient formulation for the simulation. Okay, it is important this option here, warp phase gradient correction. It is enabled by default because the mesh I'm using. I didn't explain that, but I did the mesh in the Fluent Meshing workflow. If you want to know more about how to use the Fluent Meshing option, then I invite you to see a previous video we upload in our YouTube channel explaining how to use the Fluent Meshing workflow. Okay, then I invite you to see that video and understand better, or just to have more knowledge on how to use the Fluent Meshing option. Okay, then I did this mesh using Fluent Meshing. These are polyhedral hex elements or cells. Then that's the reason, because the warp phase gradient is enabled by default, and I will left that like that. Okay, then I have some controls. This is very important for the convergence of the solution. If you have problem in convergence or you are a diverging solution, then you can change these controls and try to relax the solution. Okay, then I have to initialize the simulation, and for that we have to do a batch processing. Okay, it is very simple. Then remember that the liquid fluid it is going to be just to up to some some levels. Okay, and that's the free surface, and from that surface the only fluid that is going to be is water. Then I have to initialize the simulation with that. Then let me show you how to do it. Then a way for do that is going here to adapt, refine coarseness, and set register, a new region. Okay, then you define your region. In this case, for example, I'm going to use a cylinder shape, and I'm going to prescribe a radio, just let's say 2 meters. Okay, and from the minus y, I'm going to use -1, and here I'm going to use, let's say, 1.15, and that's it. Just save and display, and you see that this region is now created. Okay, then I'm going to close. It's okay, and as you can see, I'm going to use it for patch my solution. Then I'm going to use it. I'm going to do the following. Okay, then I'm going to use all songs, and I'm going to patch all as air. Okay, everything is going to be air. I'm going to initialize it, and once I do that, if I go here, I just create some planes to see the volume fractions, and you can see here that the only phase that is in this moment in the bioreactor is air. There is nothing of water. Then I have to change that. Then I'm going to patch. I'm going to select the region. This is a previous region I created. Is the same one. Okay, I select it. I select here air volume fraction, and I want to remove the air. I only want to have water in this region. Then I put 0 and patch. Okay, then I reload contour, and you can see that right now I have water here, I have water, and here I have air. Okay, then I have my initialization. I I can put here a value of velocity, a very low value for the mixture in the domain, just for have maybe a more efficient or a more smooth solution at the beginning. Okay, then I'm going to initialize again. As I did it, I have to patch again, and 0 errors, fraction 0, and that's it. Okay, then I'm going to run it. I will check it, and no recommendation to make this time. Then we just click calculate. Okay, and we wait until we have let's say a solution. Okay, I'm going to stop it and to wait this to finish, and I will show you what I got. Once the simulation ends, I got the solution. I am at this moment in the CFD pose. Then I have already create a plane. This is this one. It is a plane, XY plane in the center of the Airlift Bioreactor. Then from here you can predict or calculate or see different flow fields. For example, I'm going to change the view. In this case, I'm seeing the velocity, the mean velocity uh, in the actual direction. Then you see here that you have the velocity that is in the upward direction. Okay, then you have how all this is varying. But if you don't want this to see this one, for example, you can go and change the variable you want to use. For example, let's see the air volume fraction. Okay, and you see here the free surface. Here is only air. The air is going upwards and exit the domain from here, and you see how the air is moving into the Airlift Bioreactor. For example, let's see. This is the mean value. For example, here you have a like a local or instantaneous value. Let's say that remember that I did a pseudo transient simulation. Then this is like a local value for one iteration, and this is like the average. Then you can see that it's a smooth contour. Okay. Also, you can see different flow fields. Let's say turbulent kinetic energy. That is a very important one here. Well, we can change here our from 0, let's say 0.5, just to have more contrast in the color. Okay, if you want to see, let's say, wall shear, you want to see wall shear, it's important also. Okay, then you have here the wall shear values. Okay, let's see local, and that's it. The wall shear, and of course you can plot wherever you want. Then this is very important for the for the bioreactor designers that can see this kind of float fields that experimentally is not easy to measure or to see. Then of course you can do different studies and help to improve your designs. In this example I showed here in this video, I only did the simulation of the fluid. The next part, once you have your model validated, then you can include the movement of the algae cells and see the trajectories and see how you can change the the model, the dimensions, or which changes you can do in order to improve the behavior of the bioreactor, which, as I said before, is somehow related of how the cells move inside the bioreactor. Then, from this model and from this methodology I am presenting you, of course, a basic uh, tutorial or video, you can begin to try to model your own bioreactors and prove and detect which are the model that best fit to your requirements and obtain a very good model which can help you to do virtual prototyping and scale up processes. Okay, well, what I'm going to do right now is to change and show you the second geometry. The second one is another way to simulate this kind of bioreactors. It's a lower computational resource consuming, but it has some tricks and tips that I want to explain you. Okay, then I'm going to change and let's do it. Okay, then I have here the second geometry. As I told you, was this is just a half of the complete geometry. I am going to use this one. I prescribe a polyhedral mesh. Okay, this is the sparger, and this is the drag tube, the inner one, and the outer one. I also I'm going to use here, as you can see, this is shorter than the previous or the geometry number one is because in this part I'm going to use a degassing boundary condition. Okay, I am not going to model the freezer phase um, form among the mixture of water and air and the air. Okay, then in the general basis I have a pressure-based model and a steady state one of also I'm going to use a stable transient formulation. I have enabled also the gravity. This was also enabled in the for the geometry one in the previous model. Okay, now I have enabled the multi-phase model, but the difference in this case is that I am going to use the Illyrium model. I am not going to use the volume of fluids. Then this is a more accurate model, but it's also a more time and computational consuming model. Also, it is difficult to have smooth residuals and convergence, then it's very important to have a good mesh. Okay, I'm going to use the implicit formulation. Again, if I want to use the explicit, I need to change the stimulation to a transient formulation. Okay, I have to number of Illyrian phases, the water and the air. I define them here. I have the water as the primary phase and the air as the secondary phase. Here in the phase interaction, do we have more options to prescribe in comparison to the BOF model? Then I use I'm going to use uh, the drag force for and I'm going to calculate the drag coefficient by the universal drag formulation. I'm going to use the H.L.J.M model for the lift coefficient. The Weltevrode equation is untaught at all. The turbulent dispersion by Burns et al., the turbulence interaction by Sato. I'm not going to use the virtual mass coefficient and the surface tension coefficient. I'm going to model it as a constant and with a value of 0.072 as I said in the previous model. A better and in-depth study must be done in order to accurately um, have the correct value of the surface tension coefficient. Okay, this is just for demonstration. I'm going to use this. Okay, heat and mass reactions. There is nothing of these options, and in the interfacial area, the water air is this option EA particle. Okay, something important here. If you see in the air is this one. I'm going to use the diameter of 0.001 meters. Okay, this is related to the value of diameter of bubbles of air that is reported by Leeuwen. Okay, then that's the reason I use this diameter. Then I apply it. Okay, and I go to boundary conditions. Then one important thing here is that I have a degassing boundary condition. This is this boundary condition. Then all the air that arrives here will be exit of the computational domain. Then that's the reason I am not going to model the free surface, because the degassing boundary condition is acting as that interface. Okay, I have the inlet is the same, the sparger velocity, the water will not have any velocity. Here, as I am using the Eulerian formulation, then I have to define the velocity for each of these of the phase. Then I have 0 because I don't want the air enter into the domain, and here I have the velocity of the air. Okay, then remember I also have to declare the volume fraction of the air at the inlet, as we did it in the for the BOF. Okay, and if I click here inside over the sparger, nothing but the default values I am going to left in the simulation. Okay, then in this case I have a symmetry boundary condition, that is this wall, because this is the symmetry boundary condition in order to account that the full geometry. Okay, and that's it. These are our boundary condition. The method, I have the couple, and I have the pseudo transient and the warp phase gradient corrections. And one thing very important here is in the initialization. Okay, then if I go to initialize, I in this case I don't have to do the patch process, because I don't have the interface among the mixture and the air. Here everything is a mixture, then I don't have to patch. Then you can use a hybrid initialization, or you can use a standard initialization, for example from the sparger, and you can put let's say that everything at the beginning is water, and that the air velocity is this one. Maybe you would like to use a lower value, because at the beginning you want to have a better convergence of the simulation. Then you initialize, and as you see, the volume fraction of air, then you will have that everything in this case is like okay, so this is the one, that everything is like water. Okay, there is no air in the domain here. If you remember in the last geometry, in the geometry one, here we have a more standard geometry, and here was the interface among the mixture and the air. We don't have that here. This is the gassing boundary condition, and that's the reason that this geometry is shorter than the geometry number one. Okay, well, right now then you run your simulation. A very important thing is that I am going to use a lower time scale factor. I'm going to use a value of 0.2. This is because to have a better convergence of the simulation. Okay, then I click on calculate, and as in the previous example, I'm going to wait until the simulation ends, and I want to show you the the results. Okay, I'm sorry. Well, the simulation has ended, and I am right now in the CFD pose. As in the previous case, I am going to use a plane. This plane is over the symmetry boundary condition, or the symmetry surface. Then here I am showing you the air velocity, the mean velocity. Then look, here is the profile, the contour. You can see it. It is somehow similar to the one we got in the previous geometry, but remember that here this is a demonstration, then a mesh independent study, and a validation of the model must be done in order to have more accurate results. Okay. Also, if you want, you can see, for example, let's say the air volume fraction. Okay. Then here you have the air volume fraction, how the air is diffusing on the Airlift Bioreactor. Also, this is what a local or instantaneous value. This is the average. Then you see that the contour is more smooth than for the local value. Of course, you can see more flow fields. Let's say the water wall shear. And you have it here again, as in the previous case. Okay. Also, let's see if you want, for example, see no something here. You have the water turbulent kinetic energy, and this is a very okay. That's the reason we can change here for, let's say, 0.2. I don't know, have more values, but here the higher values are in the sparger inlets. Then you can change the range of the of the legend in order to see a more accurate distribution, like this 0.001. Okay, something like that. Okay, yes. Then you can play it with the with the value of the range and see how the it distributed. Of course, remember, this is just a demonstration. If you want a more accurate solution, you have to do the validation, the mesh independence study in order to have a more accurate model. Okay, this is just a demonstration on how to set up and prescribe this kind of models. Okay, then some loss of accuracy may be observed in the results in some fields of second and third order, maybe. Okay, of course, you want to see, let's say, pressure. You can do it also. Then you have different options here to play with and to see how the flow fields are are in this case behave and do conclusions and do improvements and helps your design process to be more accelerated and more successful. Okay, well, that's it. I don't want to stand me. I think the idea of this video was to show you two ways of simulate or how to simulate this kind of bioreactors, to show you how CFD can help in the design process of bioreactors. And I think it's a very good starting point for you and to develop your skills. Well, I hope you have enjoyed this video, you have learned some basics, and that this video help you to start in the bioreactor designing process and help you to improve your successful in this area. Remember, this was Jesus Ramirez from Singularity Engineering. If you have any question, please let us a comment or visit our website or call us to our phone number. Remember, we are Singularity Engineering and we are here to help you. Bye bye.